Welcome to your third section in week 3. In this time together, we're going to extend our discussion about hypothesis testing and talk a little bit more about the assumptions that underlie the statistical test that we choose. So, as you're probably getting more and more excited about the data and seeing how powerfully these tools, the descriptive tools are and the confidence intervals are to describe the data and show differences between groups, I'm going to want to take a second to pause for a moment and remember, before we can analyze effectively, we have to start back with our question. What is the question that's driving our analysis? Because once we understand the question, then we know what variables to consider, and we have to explore them. We have to look at their distribution, central tendency, variance, and then the relationships of how they're linked to each other using correlation coefficients or scatter plots. So all of these tools we've been talking about in the course are strategies to help us understand the data so we can then move to analysis. We can compare groups, we can make conclusions that inform practice and policy. But it all starts with drafting that effective question. So for the purpose of this discussion today, we're going to talk about the relationship between discharge teaching as a predictor and readmissions for heart failure. So we're trying to understand how these two are related to each other. And in order to do that, we need to first effectively describe each of those variables. Their distribution using things like histograms, central tendency with means or medians, their variance, how much difference there is around the measure of central tendency, with a standard deviation for normally distributed data or interquartile range for non-normally distributed data, and then look at the relationships of those two variables to each other. Once we understand them individually, let's begin to put them together with a scatter plot or perhaps correlations. So their inferential statistic is going to follow our descriptive statistics. We have to understand how the data are arranged before we create an analytic plan. So let's go to SPSS and understand these variables. So with your data set open, your analytic thinking cap on, let's open the Analyze tab and go to Descriptive Statistics Frequencies, where we spent a lot of time. And here I've populated it with heart failure readmission numbers and discharge instructions given. Let's go to statistics and tell it we want quartiles for the median, and for the mean we want the standard deviation. So that will give us data on not only a measure of central tendency but also the variance around that measure. And that is essential, since unless we remember, we don't know how these data are distributed. So we need to figure that out before we move forward. So we'll ask it to give us histograms that show the normal curves, because those will help us to understand the data distributions. So let's run this analysis. All right, so here we have heart failure readmission numbers and discharge instructions across the top. And then we have our measures of central tendency, the mean and median, followed by our measures of variance, standard deviations, and our percentiles, which would give us our interquartile range. So if you look at those data, you can compare means and medians and get a sense of how the data are distributed. But when you have a visual diagram, it's equally, if not more effective in showing you that distribution quite quickly. So if we look at this depiction of the heart failure readmission numbers, we see that the majority of the observations happen on the left-hand side of the graph, and we have a tail going off to the right. So, of course, those data are right skewed. And now we look at the proportion of hospitals giving discharge instructions. These data, the majority of the observations are occurring on the right, and then there's a tail that goes off to the left. You can see a few blips here, here. So very few observations at the lower ranges. But that indicates that these data are left skewed. So the next question is, based on this understanding of the distributions, which measures of central tendency would be the best to describe our data? And then by extension, which measures of variance would be best to describe these data? So think about that. Come back and join us with your answer. So as you've thought about that, excuse me, as you've thought about that, and you see that both of these variables are skewed, that would tell us that the median is going to be the most effective measure of central tendency. And here, for heart failure readmission numbers, our median is 66 and our standard deviation is 81. So if we wanted to know where do 95% of all hospital readmissions for heart failure lie, it would be between excuse me, between the mean of 90 plus 2 standard deviations above and minus 2 standard deviations below. So if we wanted to understand measures of central tendency for non-normally distributed data such as these, we would use the median of 66 and the interquartile range, which goes from 25th percentile of 32 to the 75th percentile of 121. So if we were describing these data, we could say, when considering the total number of hospital readmissions for heart failure in the United States, facilities have a median number of 66 readmissions with an interquartile range from 32 to 121. And that very brief statement gives us a quick picture of what is depicted in this graph. So now that we have these measures of central tendency and variance, we can move on with our final stage of analysis. And in that stage, we're going to look at the relationship between these two variables. We already know that they're not normally distributed, they're skewed. So let's see how they compare to each other, how they relate to each other, rather. So let's go to Analyze, and we'll come back there. Pardon me. We'll go to Graph first to depict this visually. Let's go to Chart Builder, and let's select the scatter plot, first one on the left from the gallery, and we're going to compare discharge instructions to the total number of readmissions. I'm going to select those from the variable menu if they're not already populated, and then I'll say, okay, let's see this graph. Now here, you can see that for facilities that have a high proportion of discharge instructions given, most of the observations are clustered here, so that between 90 and 100% of hospitals are giving the majority of instructions. Rather 90 to 100% of facilities are giving discharge instructions, so they're very frequently giving discharge instructions. And when we look at the number of readmissions, we can see that the higher we go on the y-axis, the more readmissions we have. So here we have 100% of facilities giving discharge instructions, and yet this facility has about 850 readmissions. You can see here, again, 600 to 700 readmissions with a very tight clustering of data points here in the 90 range. So is there a relationship between these two variables? There clearly is, but is it a strong relationship? And you can look at this graph and see that the relationship between the two is actually quite weak. So we can quantify that relationship further by going to Analyze, and then within the Analyze menu we can select Correlate, and then Bivariate. So I'm going to select the two key variables we're interested in, and we'll use a Spearman's correlation coefficient, which is for non-normally distributed data, a rank correlation, and a Pearson's correlation, which is for normally distributed data. So we've looked at the data, and we would expect that Spearman's will be the best description of the correlation between these variables because it's based on rank and not absolute value. So let's run the analysis and see what we find. So if we go and look at the non-parametric correlations, we're going to find Spearman's rank correlation coefficient here. And this is the heart failure readmission numbers and the correlation coefficient with discharge instructions given. So you can see here the correlation coefficient is 0.047 or 4.7%. So it's a very, very weak relationship. And it indicates that the more a hospital, the higher proportion of hospitals that give discharge instructions are going to have more readmissions. So is that some sort of a spurious correlation? We'd expect if discharge instructions decrease admissions that giving discharge instructions would actually decrease our number of admissions. But we'll talk more about that later, whether or not that's a spurious correlation based on the skew of the data or based on the volume of the facilities, since heart failure readmission numbers is an absolute number and not a ratio of admissions to discharge. But that's discussion for future. For now, we just see that there's a weak but positive correlation between discharge instructions and readmissions. Now, when we compare that to the correlation coefficient for normally distributed data, the Pearson correlation coefficient, we see that Pearson suggests that there's a stronger relationship between the two of 11.2%, but we know that that is not a clear or powerful measure when the data don't match the assumptions of that test. So we've seen by example how the inferential conclusion that we reach based on a parametric or a non-parametric test can be different when data are not normally distributed. So it reinforces our principle that inferential statistics always follow descriptive statistics. We always have to describe our data first. So now let's go from that general concept, seeing it in action, and talk a little bit about assumptions. So every statistical test has assumptions, and here are the key assumptions for a t-test. So a t-test is for normally distributed data. That's a key feature of this test. It tests the null hypothesis that the mean of group 1 is the same as the mean of group 2. So if we have a p-value of 0.20, it suggests that the mean of the two groups are statistically not different or statistically undifferentiatable. So we can't conclude that their means are different when our p-value is 0.2. It doesn't meet the standard criteria of 0.05 or less. So that's the assumption about distribution that it's normal. It tests the null hypothesis that the mean of group A and group B are equal. And it also assumes that you're using interval or ratio numbers. So state is not interval or ratio. It's a nominal variable. It's just a name. It's not a sort of a sliding scale or a number, a continuous number. And the t-test also assumes that you're testing differences between two groups, not more than two, and the observations of the groups are independent. So let's run a t-test on the data that we've been looking at. We already know that the data are not normally distributed, but I want to illustrate how to run a t-test. I'm not saying that the t-test is the right one for these data, but I simply want to illustrate the process. So back in SPSS, we'll go to Analyze, and we are going to compare means, independent sample t-test. So that's comparing mean between two groups. And I'm going to say, let's look at hospital heart failure readmissions, except not excess. We have the total number of heart failure readmissions, and we've stratified it by discharge instructions. I got to that stratification by selecting discharge instruction given and define groups with a cut point of 90. So looking at my data, I think there might be a difference between hospitals with a high proportion of discharge instructions and those without. I'll run this, and we're almost out of time. But you can see here in the statistic in your output